What we want to discuss now is the notion of a root of a polynomial. This will lead us to the concept of factorizing polynomials and how we do that, and in particular to what's called the fundamental theorem of algebra. So here we go. So first, the formal definition. A number, which we will denote, let's say, by x0 to emphasize that it's not a variable but rather a specific number. A number x0 is called a root of a polynomial of p of x. P of x is a polynomial if, when you plug x0 in, you get 0. Okay, so let's start right away with an example. Remember that we said that when we're working over the complex numbers, it's more traditional to use the letter z rather than x. So z0 equals 1 is a root of the polynomial. Let's call it a root of the polynomial, let's call it q of z, which is z cubed minus I z squared minus z plus I. Okay, so why is that true? Because if we plug in 1 here, we would get 1 cubed, which is 1. 1 squared is 1, so we have I times 1. So we have 1 minus I minus 1 plus I. 1 minus I minus 1 plus I, so we get 0. Okay? Because since q of 1, when we plug in 1, we get 0. So that's the notion of being a root of a polynomial. Another example. Let's look at the polynomial p of z, which is z squared plus 1. And if you think about it a bit, I think we even mentioned this specific example, does not have real roots. So there are no real numbers that we can plug in here and get 0, because every real number, when we square it, we get something non-negative. When we add 1, we get something strictly positive, and therefore we could never get a 0 when we're working over only real numbers. However, z0 equals I is a root. That's how I came to the world, right? So I squared is negative 1, and therefore negative 1 plus 1 is 0. So 0 equals I is a root. Are there any other roots, by the way? Very good. Negative I, so is, let's call it z1 equals negative I. Negative I squared is negative I times negative I, so it's plus I squared. I squared is negative 1, so we get again negative 1 plus 1, and we get another root. Okay, so these two numbers are the two roots of this polynomial, but only if we're allowing our world to be the world of complex numbers. If our world is limited to the reals, there are no roots. Okay, here's another definition. X minus x0, an expression of the form x minus x0, is called a linear factor in the context of polynomials. The reason it's called linear, because when we discuss functions, and that's more of a topic of your calculus course, but you have seen functions before, you know that something like this, f of x equals x minus something, is a linear function. Its graph is a straight line. And this is called a linear factor in the context of polynomials. So if we take a polynomial and can break it into pieces that contain factors like this, then what we're doing is factorizing. Let's say that. So first let's remark, in fact, this expression by itself is a polynomial of what degree? Right, of degree 1. And a product, so this is the end of the definition. Now it's just a bit of observations and remarks. A product of n linear factors let's write such a product. So x minus x0 times x minus x1. Remember, the x is the variable, okay? The x0, the x1, and there's going to be an x2, and so on, are fixed numbers in concrete examples. We'll do one in a minute, okay? So we're multiplying n of these. So the last one is going to be x minus x sub n. So a product of n of these is what? Well, if you think a bit, if we open all these parentheses, right, we do the multiplication, and it's going to be a bit of work, right? We have to do it carefully, but what's going to emerge here is a polynomial of degree n, okay? So we're going to have, if we take from each of these the x, we're going to have x times x times x n times, so we'll get x to the power n, and then when we take the numbers, we'll get x to lower powers with some coefficients, okay? We'll do an example in a minute, you'll see it, it's very obvious. It may be confusing in this abstract notation. So a product of n linear factors, I'll write it in a minute, is a polynomial of degree n, where each of these numbers are roots. So let's call it p of x. If you're going to plug in an x0 here, this linear factor will become 0, because x0 minus x0 is 0. And then it's multiplicative, so it will make the entire thing 0. So x0 is a root. P of x0 is 0. So is p of x2, so is p of xn. Okay? So a product of n linear factors is a polynomial of degree n, for which x1, we started with x0, for which, oh, so we took too many of these, right? Yeah, we took n, oh, sorry. Let's go back one board for a second. If we start from x0, then we're going to have n plus 1 factors here, and it's going to be a polynomial of degree n plus 1. So let's remove the first one and just start it from x1. P of x equals x minus x1 up to x minus xn. Now it's a product of n factors, is a polynomial of degree n, for which x1, x2, all the way to xn are roots. Example. Let's quickly do an example. Whenever you encounter a new term or a new definition or a new notion, always look at down-to-earth examples to understand it. That's always the way you do things in math, even when you get very far down the road. Okay, you always start by looking at local little examples and understanding the phenomena and gradually taking it further until you get to the abstract world. Okay, so here's a concrete example. Let's look at z plus 1 times z minus 1 times z minus I. So this is going to be a polynomial of degree 3, right? So let's see what we get here. But you can right away see that negative 1 is going to be a root, because if you plug in negative 1, this is going to become 0, and therefore the entire product is 0. As is 1, and as is I. Okay, so those are the 3 roots of this polynomial. Let's simplify, or I don't know if that's the correct word, because this is, from some perspective of knowing the roots, this is its simple form. Let's convert it to its standard form of an x to the n plus an minus 1x to the n minus 1. So let's first multiply these two terms. Z plus 1 times z minus 1 is z squared minus 1 times z minus I. That's this one, right? And then let's take one further step. So we're going to get z to the power 3 from here, z to the power 3, minus I times z squared, minus I z squared, minus z, and plus I. So this is this polynomial. If you look back to the first example we started with, this is q of z that we mentioned earlier. Okay, so in fact, what happened here is that we factored q of z as a product of 3 linear factors. Okay, so this is good old q of z from the beginning of this discussion, and its roots, the roots of q of z, which may not have been obvious if you look at this form, but if you know, and how do you know is a big question, but if you know how to go backwards, if you know to start from here and to get to this point, here the roots are obvious. The roots of q of z are 1, -1, and I. Those are the 3 roots of q of z. Okay, good? Okay. By the way, we already verified that 1 is a root. You can verify here if you want to really be convinced, but this should convince you just as well, that if you plug in I, you get 0. Okay, that I in fact makes this expression 0. Here it's straightforward, right? Here you need to calculate a bit. Okay. So how do we factor? How do we find the factorization of a polynomial? Does it always exist? Well, the first answer, the second answer, does it always exist? We already know. It depends on over what field you're working. Where are you allowing your numbers, your coefficients, and your roots to be taken from? Because we've seen that, for example, z squared plus 1 does not have real roots. Okay? So let's do a couple of examples and then state the theorem that says that over the complex numbers, all roots always exist. So let's do first an example. So the question is, or the title is, finding roots. Or another way of saying it is factorizing. That's the title. And let's start with an example. So suppose we have p of x, a polynomial x squared minus 6x plus 5. So how do we find the roots? For example, we can look at the quadratic formula. The quadratic formula would tell us what are the roots of this expression, and then we can write it as a product of linear factors corresponding to those roots. So let's do this real quickly. This is the way I'm accustomed to using and writing the quadratic formula. There may be other ways, it's fine. So x12 means that those are both roots written at once. So it's, let me remind you of the formula. Minus b plus or minus the root of b squared minus 4ac. This is called the discriminant, divided by 2a, where a is the coefficient of x squared, b is the coefficient of x, and c is the free coefficient. Let's plug in the values for this one. So b is -6. So -6 is 6 plus or minus the root of b squared is 36 minus 4 times 1 times 5, which happens to be 20, divided by 2 times 1, the leading coefficient. So it's 2. So what we get is 36 minus 20 is 16. The root of 16 is 4, so we get 6 plus or minus 4 divided by 2, and this leads to the 2 roots. Let me write it again here. So this equals 6 plus or minus 4 divided by 2, And again, this is the way I'm used to writing it. So 6 plus 4 is 10 divided by 2 is 5. That's one of the roots. And 6 minus 4 divided by 2 is 2 over 2 is 1. So these are the two roots. And what this means is that, so therefore, p of x can be written as x minus 5 times x minus 1. That's the factorization. These are the roots. And this are two different ways of writing the same thing. There are other ways of finding this form, the factorized form from this. You may have seen them. I won't review them now. There's a method called completing the square. There's a little guessing game you can play, and usually if the numbers are nice, get to this form. And there are a few other trickier methods that we'll mention later. But this would always work, always, as long as you're working with a polynomial of degree 2, okay, which is rather simple. Okay, so that's the factorization for this one. Let's do one quick other example. So if you look at p of x equals x squared minus 2x plus 1, and carry out this calculation using the quadratic formula. I won't do it again. You all know it, I hope. You would see that this factors as x minus 1 times x minus 1. Once you have this, verifying this is very easy, right? It's x squared minus x, so minus 2x plus 1. So here, we got a slightly different situation. There are two factors, two linear factors, but in fact they're the same. Okay, so there's only one root, but it has what's called a multiplicity. Okay, so the root, so let's write it, x equals x1 equals 1 is a root with, and the term is multiplicity 2. So there are two of them as roots, but they're the same. Okay, and it's not. We'll see later that this is important. Okay, you can't just say there's only one root. It's one. It's important that it appears twice for many things that we'll do later on in this course. Okay, so that's this notion, and we've seen an example where there's no roots. Okay, this would correspond to the situation where the discriminant, the expression under the root sign, is 0. That's what's going to happen if you do this calculation. And there's, of course, the situation where there are no roots, where the discriminant is negative. No roots, meaning no real roots. Okay? Over the complex numbers, when we're working over the complex numbers, there are always roots. And that's called the fundamental theorem of algebra. Let's write it down. So, the fundamental theorem, only one theorem in every kind of branch of mathematics gets the honor to be called the fundamental theorem. There's the fundamental theorem of arithmetics, and there's the fundamental theorem of calculus, and this is the fundamental theorem of algebra. And what it says is that every polynomial of degree n over C, meaning we know and we're allowed to work with complex numbers, both for the coefficients and for the roots. Our world is complex. That has several interpretations, but what we mean is that we're working in the realm of complex numbers. So every polynomial of degree n over the world of complex numbers has n roots. And when we mean n roots, we don't necessarily mean n distinct roots. They may be with multiplicity, like in the last example where the root was a single root but had multiplicity 2. So let's write here counting multiplicity. So if a root has multiplicity 2, we consider it as 2 roots. Proving this theorem, we mentioned it several times, I think, goes beyond pure algebra. So in order to prove this theorem, the standard proof actually uses tools taken from complex analysis, and therefore we're not going to present the proof here. Usually if you take a course in complex analysis, one of the theorems that you see is in fact a proof of this fundamental theorem of algebra. So the big question is, how do we do it? And the proof does not give you a recipe. Okay? So how do we, given a polynomial, how do we find the roots? And that turns out to be a very, very intriguing question. And people have struggled with it even before they knew of complex numbers. People meaning mankind, mathematicians, both professional and amateur, have struggled with this question for many, many years. And so let's write down the question and then say a bit of how to answer it. So, question: how do we find roots? And the answer starts out as being very easy, but then gradually becomes more and more complicated. And what do I mean starts and gradually? I mean when we make n bigger and bigger. So for n equals 1, n equals 1 is a polynomial of degree 1. So for n equals 1, what's a polynomial of degree 1? It's just something of the form ax plus b, right? That's what a polynomial of degree 1. And the root is kind of just looking at you. How would you make this equal to 0? So the root is x1, and it only has one root. And it's always going to have a root, no matter what field you're working on. The reals are the complex numbers. The root is going to be, this has to be 0, so x0 has to be minus b over 8. Right? If you take minus b over 8, plug it here, you get 0. So that's the situation for n equals 1. For n equals 2, we have the, so this is a polynomial of the form p of x equals ax squared plus bx plus c. And how do we cope with this one? Right, we've just seen it. It's the quadratic formula. So we have the quadratic formula. For n equals 3 and n equals 4, it turns out that there are also formulas. Okay? So for n equals 3 and 4, there exist, so this is the mathematical symbol for there exists, formulas. And the reason I'm not spelling them out for you, and the reason that you probably have never seen them written down, is that they're very nasty. So the formula for degree 3 is in fact a sum of two gigantic third degree roots, inside which you have expressions that are big and use all the coefficients. There are going to be an a, a b, a c, and a d, right? ax cubed plus bx squared plus cx plus d, and all of them appear inside quadratic roots and third roots and square roots, and it's a bit of a mess, but it is a formula strictly by radicals, just like the quadratic formula, and you can plug in the numbers. And we've mentioned before that this formula was discovered by two Italian mathematicians in the 16th century named Cardano and Tartaglia. Those are Italian names. Tartaglia was the one to actually discover it. He didn't publish it. Cardano was the one to publish it, and in fact, because Tartaglia told him it as a secret, and he promised never to publish it, but he did. And in fact, there's an interesting story of a kind of interesting soap opera that goes along with that. You can read it on Wikipedia if you want. But the point is that there is a formula. A student of Cardano discovered the formula for polynomials of degree 4. That's even blah-ier. And in fact, they were both published in the same book written by Cardano. So the formulas exist. And then the remaining question was, what do you do for n equals 5, or in fact, for n greater than or equal to 5. And once these formulas were discovered, people were kind of sure that these formulas exist, but they were also convinced that they're probably very big and scary. And therefore, they worked and worked and worked and tried to find them. And it was only in the 19th century, around 1820, that it was determined that there is no formula by radicals for polynomials of degree 5 or higher. So no formula by radicals. So it doesn't mean that you can never find roots. It means that there's no closed formulas where you can just plug in the coefficients and boom, do some calculations and get an answer, which would be very nice because today we could use a computer and do it very easily. But it doesn't exist. And proving that things don't exist in mathematics is usually the hardest problems there are, because you have to somehow show in a way that's nobody could argue with you. Not even in 100 years an alien from outer space would come and say, hey, you just missed it. Here's the formula for degree 5. No, it cannot exist, okay? And the people that proved this, it's in fact attributed to 3 people. One was called Ruffini. He in fact showed, but he had gaps in his proof, but he kind of gave the basic ideas in I think it was in 1799. And then 2 mathematicians filled in the details and did it in a fully correct way, and in fact explored which polynomials of degree 5 do happen to have formulas and what are the conditions. And this seemingly very easy question that we can pose the question right now turned out to be the birthplace for a vast topic in mathematics called group theory. We mentioned what a group is at the beginning of this course. Before we mentioned what a field is, we said what a group is. And the entire topic of group theory, which is today very, very extensive. Many people make their living off it, and it's related to many, 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 many fields of mathematics and applications of mathematics, started with this question. And the people that are responsible for it are a Norwegian mathematician named Niels Henrik Abel. For him, we have the name of Abelian group, if you remember. And the other mathematician was Évariste Galois, a French mathematician. Both have very interesting life stories. Both died very, very young. They kind of have similar life stories, in fact. Both at first thought they actually found the formula, then found a mistake, and then were led to understanding that there actually is no formula, and then published their results. I do recommend, if you like the soap operas behind this, the story, especially of Galois, is very, very interesting. The guy was a revolutionist in his free time. Well, I'm not sure what was his hobby and what was his occupation, if he was a revolutionist. We're talking France in the early 19th century, revolution, Napoleon, and all kinds of, and the monarchs. And so I'm not sure if he was a full-time revolutionist doing math as a hobby or vice versa. You can argue about that, but the point is that he had a tremendous contribution to math in terms of Galois groups and Galois theory, and he died at the age of 20. It's just unbelievable. And he died in a duel, probably fighting over a girl. And the night before he died, he was sure that he's going to die tomorrow. So he sat down all night and wrote a lot of math and a lot of letters to his fellow revolutionists. And yeah, so that's the story of Galois. Please read about him. It's very interesting. The point is, no closed formula. So what do we do? So having answers for 1, 2, 3, and 4 is maybe sufficient for playing, but you can understand that in real life, polynomials of degree 17 or 170 or 17,000 also show up and play important roles in various kinds of applications. What do we do? So the answer is, and that's what we're only going to kind of give hints to right now, is that there are some tricks that enable us to usually partly play guessing games and then carry out some tricks in order to find roots. So let's maybe write that. But at the end of the day, it's all kind of numerical methods of approximations and finding the roots in methods that are available today because of computers. So let's write that. There are various tricks. So these tricks are really theorems and require proof, but they only work in specific cases. They don't work in general because there is no general formula. There are various tricks for finding roots, for factorizing in specific cases. And in general, there are numerical methods, which we're not going to go into. They're beyond the scope of this course. But they do allow you to find roots, maybe not precisely, but up to a certain error. So if you can find the root, knowing that you have a mistake 15 digits beyond the decimal point, that might be sufficient, right? It might be good enough for anything practical that you want to do. So that's what I mean by numerical methods. So here are some of these tricks. So I'm going to write them maybe as theorems, mention a few of them, and then do an example or two. But that's all. So some of these tricks. So let's maybe call them theorems. So the first theorem, which you should know, I mean, so let's write it each one separately. So the first theorem is called Vietta's. The double T, I don't remember if it's a double T or not. I think it was a double T, but I'm not sure. Vietta's formulas. That's what it's called, named after a mathematician called Vietta. And they say the following. The sum of the roots. So if you have all the roots and you sum them, you get x1 plus x2 plus ... plus xn, that's the sum of the roots, equals minus an minus 1 over an. So an is the leading coefficient. An minus 1 is the coefficient of x to the power n minus 1, of the power second to the highest power, and you have a minus here. Okay? And the product of the roots, so x1, x2, ... times xn equals -1 to the power n. This is just a way of saying plus minus, because if n is even, if we're looking at a polynomial of degree 12, then -1 to the power 12 is 1. If n is odd, we're going to get a minus. So it's either a plus or a minus, depending on whether the polynomial has an even or an odd degree, times a0 divided by an. So this is the formula for the product, and this is the formula for the sum. Okay. In particular, so maybe let's mention it, for n equals 2, when you have a polynomial of degree 2, what do we get? x1 plus x2, there are only two roots, and their sum is negative. The second coefficient is b, the first coefficient is a, so it's minus b over a, and x1 times x2 is, n is 2, so this becomes a 1, and a0 is c, the free coefficient, divided by a. So this is the interpretation of Vieta's formulas for polynomials of degree 2, and this is useful, okay? This is another way. Remember, we mentioned that there are several ways of finding roots. So for a polynomial of degree 2, we often use these formulas to get the roots before trying to use the quadratic formula, which may take an extra line, okay? So this sometimes is shorter, okay? So this is Vieta's formulas. I'm not going to prove them. The proof is very easy, but you can try deriving the proof on your own. It takes more careful writing, but you may see it later in tutorial or discussion or on exercises. Here's another theorem. We just don't have time to go into the proofs of everything, so I'm going to prove one of these just as an example. So here's another theorem. So what do I mean that it works only in specific methods? This theorem doesn't tell you what the roots are. It just gives you some data about them. Okay, so Vieta's formulas give you what the sums of the roots are and what the product of the root, what the sum is and what the product is. So if you have 17 roots and you know their sum and their product, that doesn't tell you what all 17 are. It's just partial information, which may be useful if for some reason you have more information that you can accumulate and then find the roots. We'll see an example in a minute. Another theorem, if, so this even starts with an if all coefficients are rational, maybe we'll even write a more restrictive form, are integers. So this is a very friendly looking polynomial. All the coefficients are 2, 3, minus 5, 7, etc. No 1/2, no pi, and no I. Okay, only integer coefficients. And you have a rational root. P over Q is a rational root. So it's a lot of ifs here. If the coefficients are integers. And suppose the polynomial has a rational root, okay, that could happen and could not, right? Z squared plus 1 has integer coefficients, but no rational roots, not even real roots, okay? But if all this happens, then P, the numerator of the rational roots, the rational root, divides, P divides a0, the free coefficient, and Q divides an, the leading coefficient. So how is a theorem like this useful, for example? If you take a polynomial, and suppose it's not too big, like of power 3 or 4, and all the coefficients are integers, then you know that if you're seeking for rational roots, there's only going to be a finitely many of them that could be candidates. Because P has to divide the leading coefficient. If the leading coefficient is 2, P doesn't have too many choices. It could either be 1 or 2, or -1 or -2. And Q has to divide the leading coefficient, AN. Okay? So you'll see examples of how to use this. Again, this is very partial. It only works in specific cases. And the last theorem that I want to mention, and this one I want to prove because it's good practice for complex numbers. So the last theorem, we'll write it on a separate board so we can prove it. So the last theorem that I want to mention, theorem, if P of Z has real coefficients and, so this is again a restriction, does not apply to all polynomials, and Z0, which belongs to, remember this symbol belongs to C, is a root, then Z0 bar, the complex conjugate of Z0, is also a root. So what this tells us is that if we're working over the complex numbers, but we happen to take a polynomial with real coefficients, then its roots come in pairs. For every complex root, its complex conjugate is also a root. Okay, and this can also be useful. Again, we'll see examples throughout exercises and discussions. So let's prove this one. Let's write the proof. How do we prove something like this? So when we write a proof like I'm going to write, it may require to go home and read it over a second time. And you have to do two things when you read a proof. One is to follow line by line, see how every step is in fact a consequence of the previous step. Okay, so that's one thing. That's like looking at it from this close. And then you have to take a step back and see that you understand what happened here. Okay, see the broader picture. Okay, and those two things are not exactly the same. Okay, they together they form an understanding of what the proof is. So let's write the proof. So the first thing I'm going to do in order to make life easier is not to write all the time an z to the n plus an minus 1 z to the n minus 1 plus an minus 2 z to the n minus 2, etc. Because we have to prove this for a general polynomial. I'm going to use the notation of sigma. Sigma is the way, this is the capital Greek S, sigma for sum. And the way to write a polynomial like this is sigma a sub j, let's call that the index, z to the power j, where j ranges from 0 to n. So this is just notation. This is a compact way of denoting a0. So we start with 0, end up with n, and plug all these values for the j's. So this is just another way of writing. This is the same as a0 z to the power 0. Z to the power 0 is just 1, so I just write a0 plus a1 z to the power 1, which is just z, plus sigma stands for plus 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 a2 z to the power 2 plus a3 z to the power 3 plus a4 z to the power 4 plus etc. How far do we go? All the way to what's written here, to n. So plus an z to the power n. Okay? Now, If you're not used to sigma notation, what I'm going to write now is going to be even double confusing. Okay? Because sigma notation is something you need to get used to. And that takes a bit of practice and time. So if you're not used to it, you can spell out everything like this. It's just going to make every expression like this be a bit bigger. Okay? But I want to do it using the sigma notation because then everything is revealed, but everything becomes much more compact and easier to write. Okay? So don't be afraid of this sigma notation. You can get along without it, but I believe that as we progress in this course and in many others, you'll see that it's so convenient that you're going to want to get used to it, and why not do it now? So here's the proof. Here's the proof. So we're assuming that z0 is a root. What does it mean that z0 is a root? This is an abstract proof. We don't know what the polynomial is. We don't know what the root is. Everything is completely abstract. What does it mean that z0 is a root? Right, the definition. So what did the definition say? When is z0 a root? So this implies that p of z0 is 0. That's what it means to be a root. When you plug in z0, you get 0. Okay. What is p of z0? It's no longer a polynomial. P of z is a polynomial. P of z0 is a number, right? In this case, it's the number 0, right? So p of z0, when you plug in a concrete number into a polynomial, you get a number. If it's a root, you get 0. So if p of z 0 is a root, then this implies, if z0 is a root, p of z0 is 0, so we can write for the same price, p of z0 bar, its complex conjugate, is also 0. This is a number. It happens to be the number 0, so its complex conjugate is also the number 0, right? The complex conjugate of 0 is 0. Okay? Now remember what we want to prove. We don't want to prove that p of z0 bar is 0. We want to prove that p of z0 bar is 0. We want to somehow take this bar on the entire thing and throw it just into z0. That would mean that z0 bar is a root. That's what we're trying to prove. That if z0 is a root, so it's its complex conjugate. So how do we do that? So let's do it. So p of z0 bar, what is that? On the one hand, it's 0. That's what we just said. On the other hand, this is the sum, j equals 0 to n, of a, j, z to the power j. This was p, but now we plugged in z0, so it's z0 to the power j. This is p of z0, and then bar on the entire thing. Do you agree? Okay, may look scary. You may feel, wow, we're doing real math now, but let's think just for a second. Let's look back one board. Here's p of z. When we plug in z0 instead of z, we get z0. When we take the bar of it, it's just the bar of everything. Do you agree? Okay, so it's not that bad. So this is what we get. Now this is a sum. This is a bar, the complex conjugate of a sum. We know that the complex conjugate of a sum is the same as the sum of the complex conjugates. This is one of the properties of the complex conjugate that we had written last time when we discussed complex numbers. So this is the same as sum j equals 0 to n, aj z0 to the power j, and now the bar is on each term separately. This bar for j equals 0, plus this for j equals 1, plus this for j equals 2, etc. Okay, so it's bar plus bar plus bar plus bar, instead of bar on the entire sum. Good, everybody with me? Great. No question. If you have a question, if something is too fast or you can't see it, you can either stop me and I'll try explaining again. If you feel completely overwhelmed and you're seeing, then go home and read it over. You'll get it, and if not, come and ask. Okay? Good. Now I'm going to treat each of these little guys separately. So the sigma outside remains the same, j equals 0 to n. And now we have a product here. aj times z0 to the power j, everything bar. The bar, the complex conjugate of a product, is the product of the complex conjugates. Again, this was one of the properties of the complex conjugate. So I can write aj bar times z0 to the power j bar. Bar on this times bar on this. Okay? Now I'm going to use, and this is crucial, the assumption of the theorem that all the coefficients are real. If all the coefficients are real, what's aj bar? Exactly. Okay? So if aj is real, its complex conjugate is itself, right? The complex conjugate of a plus bi is a minus bi. But a real number is a plus 0i. There's no imaginary part. So the complex conjugate is itself a minus 0i, which is just a. So here I can replace j equals 0 to n, aj without the bar, z0 to the power j bar. So here I used the fact that aj belongs to the real numbers for every j. So here I use the assumption of the theorem, and I would not be able to take this step without that assumption. Okay? Now, again, what is written here, z0 to the power j is z0 times z0 times z0 times z0, j times. So it's a product, and I'm taking the bar. I can replace that with the product of the bars. So I can rewrite this as sum j equals 0 to n, aj z0 bar to the power j. Okay? Bar, conjugate of a product, is the product of the conjugates. Okay? Properties of the complex conjugate. And what is written here, this is precisely the value of p at z0 bar. P at z0 bar is taking p and plugging in z0. Sorry, plugging in z0 bar for z. Do you agree? Okay. So what we proved here is that p of z0 bar equals 0, meaning z0 bar is a root. So under the assumption that we're working with real coefficients, if you have a root, its complex conjugate is also a root. This completes this proof. Okay? Whew. Kind of abstract, kind of maybe heavy, especially if you're not used to sigmas, but in fact, very elementary, very basic. We didn't use any major theorem. We didn't throw in the fundamental theorem of algebra in order to prove this, for example. Okay? We didn't use any sophisticated result. We only used the very basic properties of the complex conjugate, proofs of which are one-liners or half-liners. We discussed them. And careful work with abstract notation, which takes time to get used to. Okay? Okay. So the one last thing I want to do is just do one. I know this turns out to be a bit long, but this is one last thing I want to do. And that would complete our introduction to polynomials. We're going to use polynomials a lot in this course and in other topics like calculus and applications of these two very basic courses. What I want to do is do a quick example of just, a bit how we use parts of these techniques or maybe others to find roots. So here's an example. Suppose we have the polynomial p of x equals, it's going to be a polynomial of degree 5. So we know that there's no formula. So x to the power 5 minus x to the power 4 minus 10x to the power 3 plus 10x squared plus 9x minus 9. Oh boy. So this is a polynomial of degree 5. We want to find the roots. Okay? So where do we start? Do we start looking at all those theorems? You could, and maybe reveal some information. For example, all the coefficients here are integers, right? So that theorem about whatever rational roots are going to satisfy that their numerators divide -9 and their denominators divide 1. Okay, so those are clues. We're kind of collecting clues. But in fact, the first thing I'm going to do here is observe. Can you see a root? Just see it. Do you see a number that when you plug in here, you get 0? Does it just pop at you? Good, very good. If you plug in x equals 1, you see that 1 minus 1 minus 10 plus 9 minus 9 is 0. So x equals 1 is a root. Okay, so you can call this an observation, or you can call it a guess. That's really what it is. We didn't use any method. It's just kind of looking at it enough and, you know, the kind of the symmetry of the coefficients, and you just guess it. Okay? So x equals 1 is a root. What does it mean? It means that x minus 1 is a linear factor in this, right? That we don't know the rest of it, but we know that this can be written as x minus 1. So x minus 1 is a linear factor. So we know that we can write this polynomial as x minus 1 times something. Okay? And how do we find the something? How do we find what the multiplicative other term is going to be in this factorization? We divide. We divide this by this. Okay? And this is called long division of polynomials. I really hope that you've seen it before. If not, I'm going to do it once in this example very, very slowly, but it's a useful tool. It's going to be used in various places throughout, in calculus and in algebra, and it's good to know. Okay? So if you haven't seen it, try to trace what I'm doing, and then practice an example or two on your own, and you'll see that it's just the same as long division of regular numbers. Okay? So I'm going to divide x to the power 5 minus x to the power 4. I'm verifying that I'm going to have enough space here, and I'm not. So let's take a new board. So I'm going to divide the two polynomials and see what the quotient is. So x to the power 5 minus x to the power 4 minus 10x cubed plus 10x squared plus 9x minus 9 divided by x minus 1. This is how I'm used to writing it. Some people write this to the other side. Some people write the result in a different place. I'm going to write the quotient here. It's just a matter of what you're used to, okay? And all ways are fine as long as it's evident what you're doing, okay? So I divide x to the power 5 by x. I get x to the power 4. I'm going to write it here. I just divided the leading power. X to the power 5 divided by x is x to the power 4. X to the power 4 times x minus 1 is x to the power 5 minus x to the power 4. And then I subtract. Okay? Do you recognize long division of numbers? It's exactly the same way you do it there. I subtract. In this case, I just get 0. So I carry down the remaining stuff. Minus 10x cubed plus 10x squared plus 9x minus 9. So I have minus 10x cubed divided by x is minus 10x squared. I'm writing it above this because there's no expression with x to the power 3, and then I multiply back. So I get minus 10, x squared times x is minus 10x cubed. Minus 10 x squared times minus 1 is plus 10x squared. And again, I subtract, and in this case, everything just dies out. This is a very easy example of long division. Sometimes it can get a bit messier. And then I have plus 9x minus 9. Dividing this by x, I get plus 9. And multiplying back, I get 9x minus 9. And I get that there's no remainder. It divides perfectly. I knew that. I knew that I'm going to get no remainder because I knew that x minus 1 is a factor here because 1 is a root. Okay? So, questions about the long division? Yes. Right. It's really a miracle, or not a miracle, it's just a very easy example that these all came out to be 0. That's not always going to be the case. Okay? Don't expect that. You could get a 5x to the power 4 here, and then it will just be more steps, and these terms here won't be missing. Okay? So good? Everybody good? Okay. So the conclusion here is that this polynomial equals x minus 1 times this. Let's write that. So our polynomial, which we called p of x, equals x minus 1 times what we got as the quotient, x to the power 4 minus 10x squared plus 9. Okay, so now we're down to finding roots of a polynomial of degree 4. That's still usually impossible, usually, although there is a formula, but we don't know the formula. However, this polynomial is special. Why is it special? Right, because there's no odd powers. X to the power 3 and x are missing. Okay, so we can write, so this is another trick. Right, it's not a deep theorem, it's just really a trick, which you may have seen. Write y equals x squared. Temporarily. So this polynomial is going to be y squared minus 10y plus 9. That's this polynomial when we write y for x squared. Do you agree? And then find the roots for this one. Okay? So the roots for this one, so this, the roots, and here you can use the quadratic formula, right? Because it's a polynomial of degree 2. And the roots turn out to be are y equals 9 and y equals 1. Okay, you can do the calculation. Very easy. So what does it mean? So we know that p of x can be written as x minus 1 from this times y minus 9. So this can be written as y minus 9 times y minus 1. But remember what y was. Y was x squared. So this can be written as x minus 1 times x squared minus 9 times x squared minus 1. Right? Good, everybody? Okay. And now we're almost done. Because this is x minus 1 here. X squared minus 9 has two roots, 3 and negative 3, right? So can be written as x minus 3, x plus 3. And x squared minus 1 can be written as x minus 1, x plus 1. So there we have it. We have all 5 roots, all 5 of which turned out to be, in fact, integers, okay, in particular real. And one of them actually has a multiplicity 2. So 1, which we found originally, in fact, is a root of multiplicity 2. Okay, so the roots are 1, 3, -1, and -3. Those are the roots of this polynomial of degree 5. Okay, so I'm going to stop here with these examples. The honest truth is that we can play around with these things a lot. There are many, many examples that take all kinds of cool detours through these theorems that we mentioned, Vieta's formulas, and the case where you have integer coefficients and rational roots, and what we proved of the complex conjugate being a root if the coefficients are real, and all kinds of tricks like we did here. And we're not going to spend more time doing that here in the lectures. We're going to move on. But it is stuff that you should be familiar with, okay? You should be able to not necessarily memorize all these theorems by heart, but to know they exist and to play around a bit and see that you can find roots in easy cases and factor in easy cases, because those are things that we do all the time in various contexts, in solving integrals, and we're not, okay? So please take some time and practice this stuff. You'll, of course, get a lot of exercises in order to do so. We're going to end our discussion of polynomials here and move on to our next topic, which is matrices.